In this video, I will provide a quick overview how to automatically create input files for generation of special quasi-random structures, SQS, using ATAT, the Alloy-Theoretic Automated Toolkit, specifically the module mcsqs. And to do that, we will use an online application which is available on this link. And it's very intuitive to use it. You will just need to upload the crystal structure, the initial crystal structure, or you can also retrieve the crystal structure from implemented search database. So for instance, let me search for rutile, just as example. I can search for the structure now, and it found all available rutile structure types in 3 databases, the materials project, AFlow, or COD, and I can now simply add the structure into this calculator. And to preview it, I can see it here that it was correctly added. So this is one option, and the other option is to directly put your crystal structure file, which can be in CIF, POSCAR, LMP, or XYZ with cell information. Okay, so now I will use this, and then I need to specify which composition mode I want to use. So if I want to change like all atomic sites at once to be certain elements and concentrations, or I can specify sublattices and give them different elements and different concentrations. And in this case, the sublattices are based on the Wyckoff symbols. So in this case, I have 2 sublattices available. Okay, so let me choose this sublattice mode, and then I have to select like for how large supercell I want to search for, or for how many atoms, this the supercell with variable shapes can have. So let me reduce this now, like for example like this. And in step 3, I need to configure the sublattices. So let's say that sublattice B, which is the oxygen, I want to keep it as it is, but the sublattice A with titanium, I want to have there, for instance, a silver. Okay, and now I need to specify the concentration of titanium and silver. So let's have it, for instance, titanium with 25% and 75% with silver. Okay, and if I would want, I can specify it also this sublattice, but let's just keep it now as this. And now I can generate the input files for ATAT. I can specify like the cutoff distances for either the pairs, the triplets, clusters, or the quadruplets. Let's just have it like this and generate the input files. And now you can see the overview of the generated files. So here is the RENT file, which contains like the structure to be searched for, and here it's defined the file for the searched supercell. And I should mention then that the available concentrations are automatically recalculated, so it is possible to find this concentration for the given supercell size, respectively for the given number of atoms. Okay, so these are the 2 files that I need, or if I want to search for any supercell, the most randomized supercell, without fixing the shape, I just need this file. And here Here it's also an overview how to run the search using the ATAT. So now I can copy these two files, just their content, and create these in my folder where I want to run the ATAT. So let's see. So here I have just empty folder. Okay, basically empty. This is the structure for the example. And now I will create this file. Oh, sorry. And I will copy the content into it, save it with Ctrl S, exit Ctrl X, and now I will also create this cell file, save the content, and I already compiled the ATAT before. If you want to see how to do it, you can find it at this link. So if you open this read more, it's this user guide on this side. And also here you will find some other useful links which explain the ATAT and search for SQS in more details. And also I should mention then that if you use the SQS structure generated by ATAT, you should cite the corresponding sources. And so you should cite these two publications, and if you want, you can cite our main application for providing this interface. Okay. And also don't forget, if you obtain the structure from the database, don't forget to check the original link of that structure and see if there is any corresponding publication that you should cite as well. Okay, so now, so here I have the commands showing how to run the ATAT. So I can generate the clusters with this, and this settings, it's automatically given by the set here. So if I include triplet and generate it again, I will have here both options. So let's just do it with the pairs now. Let me copy this. So I have generated the clusters, which I can preview if I want. And now I can run the mcsqs search. So either for this predefined supercell size, which is in this file, or by searching for the supercell, the most randomized supercell, which will have this number of atoms. So if I do this option, this search started to run, and just for the illustration I will stop it now, and I can now check the log file, which is here, and it contains the objective function for each step when it improved, and then there is the best currently found SQS structure for the given settings. So if I preview this best SQS, it looks like it looks like this, and this format I can directly put, for example, to WASP calculations. So I need to convert this into structure which is readable, for example, by the WASP or by for molecular dynamics by LAMMPS, or just I can convert it into CIF file, and that I can also do in this interface. But before I will show you that, let me just mention another option, which is the parallel execution. So I can run this search parallelly. For instance, if I write this, it will start 3 runs, and if I stop it, I can see like best structure for each run, and I can see the log file also corresponding to each run. Okay, so this is one way how to run the ATAT with these generated files, and the other way, for convenience, is that I created a bash script, and basically you will just download this script, and it will automatically, when you start this script, it will automatically create these two files, and it will run the search based on the settings that is provided here. And also you can enable the parallel execution in this bash file. So you can set the number of parallel runs here, and you can specify if you want to search for the given supercell or for the given number of atoms. And there is also short tutorial how to use this bash script. So you need to first, when you download it, you will put it into your folder, and you need to make it executable, then you will run it. And I don't do everything else will be do automatically. So let me illustrate it. For example, for the parallel run with five instances, and with this generate button, I will download the bash script. Let me call it as an example, and now I need to put it into this example folder. So let me create a new one here. And here I will insert this file. And now if I go back to the console and I go to this newly created folder, so I have here the bash, and I need to make it executable. Okay, so now it can be run, and if I run it, it will provide more detailed like information in the console, and every 1 minute it will be updated, and it will show the objective function, and in the parallel case it's always took from the log file number 1. If you just so this script also creates another file which contains the information about the objective function at each basically after each minute. So you can see how the objective function converge based on the time how long this search is running. Okay, so let it run for a while, and now let's analyze the outputs. So first thing that I would like to do is to convert, for instance, go to this main folder for this example video, and you can see already that I run it parallel 5 times, so I have here the outputs. And let's say I want to convert this structure into POSCAR output file. So I will simply upload it here, and I can see like the summary information, and you can preview the POSCAR. I can also see how the structure looks like. And I put the silver there, which has a similar color in this case. And so I can download as a POSCAR file, save it, or I can select CIF, LAMPS, or XYZ format and download it as these. And I can also download a complete package which contains all the information about the set structure, which was searched for, about the supercell, etc. Okay, let me show the console. So you can see that after 3 minutes, the objective function in log file number 1 is still the same. And this will run until I stop it with Control C. Okay, and another thing, I can see the element distribution here, and I can calculate the PRDF for this uploaded structure just with this, and I can immediately see the output. And if I need and I want to create like basically randomize vacancies or like ordered vacancies corresponding to the given element, I can remove some. So for instance, I can remove this silver and create instead of this, if instead of it vacancies like this. So the silver is gone, and I can simply download this structure if I want in POSCAR or SIF. Okay, so this is one thing, the analysis. Another analysis that I can do is to see about the convergence or the objective function. So I have 3 options here. I can, in the first option, I can upload one log file. So for instance, uh, this one, and it will automatically show. Okay, this is, yeah, there is just one step. There is just one step now because it didn't found anything better yet. But okay, let me show you the example that I ran before from this parallel run. And let's see if I upload it here. You can see how the objective function is changing with every step when it found a better objective function. And so this is one option. Another option, if you use this script, I can upload this newly created file, which shows how the objective function is changing over time. So this x-axis is in minutes, and I can see the blue curve is the objective function, and it shows me how it changed over the simulation time. And I have here some additional information that can be useful. And the last thing is when I run a parallel analysis, I can upload all the log files at once, and it will automatically show me which run had the best objective function and which one had the worst objective function. There is also a table showing the same information for all uploaded log files, and if I want, I can see also the graph with the objective function over optimization step. Okay, so that's all. We can just simply stop this case and let's see if any of this run found anything better. So I will upload these 5 log files. This I need to delete. And so no, all these run found the same objective function basically. So they converge to the same result. Okay. So I think that is all. And if I want another file, I can just simply put it here, refresh the site, and repeat this automatic preparation of the input file for ATAT for your structure. Okay, so thank you for your attention, and I hope this tool will be useful to you. and see you.